So right before we left for Thanksgiving break, we talked about how to divide two polynomials using either polynomial long division or synthetic division. And we also talked about the fact that when we get a remainder of 0 using either of those two methods, that means that the expression that we are dividing our original polynomial by must be a factor of the polynomial. We also said that that would let us know where the zeros, or one of the zeros of our original polynomial was located. And we also talked about how we could use this idea of synthetic division to help us find the various factors of our polynomial, and then we can completely factor that original polynomial that we were dividing. Now, it's a little bit inefficient if you're not sure where to look for the factors. You could use guess and check, but that would potentially take you forever if you didn't have a way of limiting the possible factors of your polynomial. Fortunately, though, there's something called the rational root theorem, and this theorem sort of minimizes the various possibilities for what the factors of your polynomial could be. It doesn't tell you exactly what your factors are. It just gives you an abbreviated list of the possibilities, and then from there you can test them to see which of the various possibilities actually ends up being a factor of your polynomial. So let's take a look at what I'm talking about. Here we've got just a regular polynomial in standard form. Don't let this notation intimidate you. All this is saying is that you have some polynomial p of x. Here's our leading term. It has a leading coefficient that we're calling a sub n. And notice we've got our variable x raised to the nth power. And that n is going to be the degree of our polynomial because it's going to be the biggest exponent. And then we're just working through our polynomial in standard form. Here's the term with the next highest degree. The ellipsis here just means that we are skipping whatever terms are in between the first two terms, and then the last two, this guy right here, a sub 1 times x, that's our linear term, because notice x is raised to the first power. And then finally at the very end, of course, we've got a sub 0. Notice that would mean that x would be raised to the 0 power, so this here is our constant term. And I just wanted to refresh your memory on what standard form of a polynomial looks like, because it's going to be important for you to identify both the leading coefficient a sub n and the constant term a sub 0 in order to use the rational root theorem appropriately. So there are two pieces to the rational root theorem that are going to help you determine what your various rational roots of the polynomial that you're looking at could be. One thing to keep in mind, that if you have an integer root, and keep in mind what the integers are, those are all of the whole numbers and their opposites. So by integer root we mean a root that is not a fraction. Grief, can't even spell integer, sorry. So integer roots must be a factor of a sub 0. Meaning that if your polynomial has an integer root, then that integer root must be a factor of your constant term. So for instance, if your constant term was 10, the factors of 10 are 1, 10, 2, and 5. So any integer root of a polynomial with a constant of 10 would have to either be 1, 10, 2, or 5. There are no other possible integer roots that that polynomial could have. The other thing that the rational root theorem tells us is that if you have a rational root, and just to refresh your memory, a rational number is simply any number that can be written as a fraction. So all integers are rational numbers, but all fractions are rational numbers as well, because they can be written as, of course, the root word in rational is ratio. So you could potentially have rational roots of your polynomial. And to find those, rational roots are going to have a reduced form, and we say reduced because of course they're rational, they could be fractions. And that reduced form is going to be of the form P over Q, where we say that P is a factor of the constant term. So P is coming from one of the factors of your constant term, and Q is coming from one of the factors of your leading coefficient. So let's do some examples, just to show you what the rational root theorem actually does for us. So let's say we have this polynomial, 3x cubed plus 7x squared plus 6x minus 8 equals 0. We want to find the rational roots of this polynomial. So first of all, let's take a look at our constant term right here. Our constant term is negative 8. So that tells us, using this first fact right here from our rational root theorem, that if there is an integer root of our polynomial, then it has to be a factor of our constant term, which in this case is negative 8. So that means we need to list out all the possibilities. Well, the factors of negative 8 are positive and negative 1, positive and negative 2, positive and negative 4, and positive and negative 8. So those 8 possibilities are the only integers that could have any way of being an integer root for our given polynomial. Then the other thing we need to look at is the ratio of our constant term, negative 8, over our leading coefficient, which is 3. Actually, I'm going to back up just a little bit because I think that might be misleading. I'm just going to write out the factors of 3 next. And of course, the only factors of 3 are positive and negative 1 and positive and negative 3. So just to reiterate what I said a moment ago, the only possibilities for having an integer root for our polynomial are these values right here. These 8 integers are the only possible integer roots that we could have. However, we could have rational roots at the ratio of P over Q, where P, the values for P are given by this list of possible integer roots for negative 8, or integer factors for negative 8, and Q comes from this list of the factors of our leading coefficient of 3. So that means we have quite a few different possibilities for the location of a rational root. For instance, it could be 4/3. It could be negative 4/3. We could have a root at 8/3. We could have a root at negative 8/3. Any of those combinations of the possible values for P over the possible values of Q could potentially be the location of a rational root for our polynomial. So there still are quite a few possibilities, but we have narrowed the possibilities down from infinitely many, if we were just trying to use the guess and check method, to, how many do we have here? 1, 2, 3, 4 times 4. So there are 16 possibilities here, so not quite so bad. Sorry, check that. There are actually 32 possibilities, but either way, 32 is far less to deal with than infinitely many possibilities. So now that we've come up with our list of possibilities, what we need to do is go through and check them and figure out which one or which ones could actually be the roots of our polynomial. So what we're going to do is we're going to test out various cases, and we want, when we plug our various roots in to our polynomial, we want to get a value of 0 back out when we evaluate the expression. So on this slide, I've copied back down our polynomial, and what we're going to do is we're going to test out some possible values for our integer and rational roots. What I'm going to do first is test out a couple of integer value possibilities for our roots, because if we can find those integer values, then we can use synthetic division to actually find the rational roots, or possibly find some of the rational roots. So what I'm going to do first is plug 1 in to our polynomial and see what I get. So we've got 3 plus 7 is 10, plus 6 is 16, minus 8 is 8. And so because we don't get a value of 0 when we evaluate this expression, that tells us that 1 is not in fact a root of our polynomial. So 1's not going to work. So now I'm going to try -1, and I'll be right back after I do that. So now I'm going to evaluate our polynomial at the value of x equals -1. So I'll get -3 plus 7, that's 4, minus 6 is -2, and then minus 8 is -10. So again, because I did not get a value of 0, that means that -1 is not an integer root of our polynomial. And you can hopefully see how this works. You would just keep testing your various integer possibilities. Now I'm cheating here slightly because I know what one of the roots is. I know what one of the rational roots is. Actually the only rational root. So I'm just going to show you how this one works. Now I'm testing the rational possibilities, again by combining various factors of the constant term, which gave us our p-values, and dividing that by various factors of our leading coefficient, which was q. And one of the values that I want to test out is 2/3. The 2 comes from our list for p, the 3 comes from our list for q. So let's see what happens when we plug 2/3 into our polynomial. So I've gone ahead and plugged 2/3 in. 2 cubed is 8. 8 times 3 is 24, so we get 24 over 3 cubed is 27. 2 squared is 4 times 7 is 28 over 3 squared, which is 9. 6 times 2 is 12 over 3 minus 8. And if we, oh, I am way out of room. Excuse me. If you add all 3 of those fractions together, it does turn out to be positive 8, and then when you subtract 8, you do get 0. So because we get a value of 0 when we plug 2/3 into our polynomial, that tells us that 2/3 is one of our roots. That also tells us that x minus 2/3 is a factor of our polynomial. And once we know that, we can then use synthetic division to factor 2/3 or x minus 2/3 out of our polynomial, and we can see what remains. So let's do that on the next slide. Okay, so I've written out our original polynomial, and we are going to divide that polynomial by the factor x minus 2/3, because we just discovered that 2/3 is one of the roots of our polynomial. Now, because x minus 2/3 is a linear expression with a leading coefficient of 1, that means I can use synthetic division here to simplify the process a little bit. So I'm going to write out my coefficients, 3, 7, 6, and -8. Wait, a little better. And let's just review how synthetic division works. I bring down the 3, you always bring down that first term, and then I'm going to multiply 3 times 2/3, and that will give me a 2. Then remember, we're going to add together the rows, so 7 plus 2 is 9. Then I multiply the 9 and the 2/3 together. It's going to give me a 6. I add together 6 and 6 and get 12. 12 times 2/3 will give me a positive 8. And of course, as we expected, That adds to 0, and that tells us that our remainder, when we divide our polynomial by x minus 2/3, is 0, which of course, as we already knew, x minus 2/3 is therefore a factor. We also know then that when we divide our polynomial by x minus 2/3, what remains is 3x squared plus 9x plus 12. And because we already know how to solve quadratic equations, what we can do is we can set this expression, this quadratic expression, equal to 0 and solve for x from there.